Hello and welcome back to Prolumnus. Today's calculus video will be going over the properties of integrals. Now, since integrals are so closely related to derivatives, since they're just the inverse of a derivative, they will be inherently using the properties that we discussed in the derivative video. If you haven't seen that, go check that out, and if not, we can jump straight into the whiteboard to look at those properties. Now, the first thing you'll want to know about an integral is that it is often referred to as an antiderivative. That, of course, being indicative of the fact that the integral is an inverse of the derivative. Now let's look at some basic antiderivatives. This right here is the sign for an integral. So let's say you take the integral of 2x. This shows that you're taking an integral, and this dx will just show what value you're taking an integral of. So here you're using the variable dx. Now that's equal to x squared plus c, where c is some constant. Because remember, if you were to take the derivative of this x squared would become 2x by the power rule. Also by the power rule, all constants available would become 0. So in order to preserve those constants, you add a plus c, since you're unsure and you can solve for those later. You could take the antiderivative of cosine of x, and you'll just get sine of x, also plus c, and the antiderivative of e to the x is just e to the x plus c. And so the same thing, since the derivative of e to the x is itself, the antiderivative of e to the x is itself plus some arbitrary constant. Now another rule that is really useful is called integration by parts. Now we'll derive this rule really quickly. So if you have two functions, u times v, and you take the derivative of them, then as last video showed, it would look a bit like this, where you would use product rule to find the answer to that. Now let's say that you subtract this term from both sides. So it leaves you with u v prime on this side with u times v prime minus u prime v on this side. Now let's integrate both sides of this. This first integral will be the integral of u v prime dx equals, since this entire thing is derivated and we're taking the integral, we can actually just take the straight up inverse of this and leave that as u times v minus the integral of u prime v dx. Now, since u prime is just du dx and v prime is dv dx, this we can actually write like this, where we have the integral of u dv, where we plug this in here, and we have a dx down here and a dx up here, and you can sort of imagine those canceling out. There's a better way to understand it conceptually, but if we're just doing calculations, it actually works out. That would be equal to ru times v minus the integral of v du. Now this is really useful if you come across an antiderivative that you can't actually find very neatly, and you can split your terms into a u and a dv, where your dv will include your integration term, and you can actually split them up to find this equation much more easily. Now we can do u substitution. Now in the same way, the integration by parts is sort of undoing the product rule with integration. U substitution undoes the chain rule for the antiderivative. So let's say that you have this integral of a form where you have a composed function, where you have a composed function, and then you have its derivative on the outside. So, in order to find this, you would take some arbitrary variable u and set it equal to g of x. If you derivate this, you get du dx is equal to g prime of x, which can be rewritten like this. And now you can see that here we can plug in u into the middle of this function, and we can plug in for g prime dx just du. So this is equal to the integral of f prime of u times du, since this entire thing would just be du. And this we can solve just like any other antiderivative, where it would just be equal to f of u plus some arbitrary constant. And then you can plug in g of x everywhere that you see one of these u's at the end, and you'll get your answer. Now think about what you're doing here when you're taking one of these antiderivatives. In reality, you're looking at a graph, some arbitrary graph, doesn't matter what the function is, and you're looking at what the area is underneath that graph. Of course, you can have negative bits as well, and those counts as negative area, and you sum all those areas up. So you integrate in order to find a function. And that function is actually a function of area, where area is the output of that function based on how far along you go along the x-axis. And whether it's immediately apparent or not, this is very, very powerful, not only for these types of functions, but for problems that you could do in other fields, which we will go over in our future lectures. Now, hopefully these properties will help you get started or do some review for integration. Uthaj will be coming out with some practice problems for these and for the derivatives, so look out for those. Hopefully that was a useful interpretation of how to go about some of these. If you liked it, please consider subscribing. If there's anything you'd like us to cover in the future, please do let us know about it, and we'll catch you in the next one.